Hello aspirants, we'll be starting revision for prelims 2026 and for that we will be starting with geography first. So in geography, one of the very fine things that I have noticed is that we study geography in different sections. We're going to join it all together over here. So in today's orientation class, I am just going to tell you some things which you will be needing for the rest of the lecture. So we'll be starting with the Earth's atmosphere. So when we look at the Earth's atmosphere, where you are standing or sitting or doing whatever you are and looking up, then what do you come across? You see, first thing you come across is the troposphere. Troposphere is just 0 to 12 kilometers, and most of your activities like aircraft or tourist balloons or most of your activities takes place within the troposphere. After the troposphere, we enter into the stratosphere. Again, 12 to 50 kilometers. And over here, what we have is most of your missiles, hot air climatic balloons. Now, these are different kinds of balloons which are used for measuring the weather patterns and other research purposes. After the stratosphere, we enter into mesosphere. You can remember mesosphere through meteors. Now, in this layer, most of our meteoritic material evaporates or just gets withered into the atmosphere. This is where it happens. That's why this layer is also known for its mesospheric clouds. We will read about this in detail when we study clouds, but this is where mesospheric clouds are formed. After that comes the thermosphere. Now, thermosphere and exosphere are those areas which are on the outer layer of our atmosphere. Much outer layer. In fact, the length keeps on decreasing and increasing also. So, this is the Earth's atmosphere. We'll go slightly in depth, and troposphere, again, lowest layer of the Earth's atmosphere. After that comes stratosphere. This is where the ozone layer is present. Remember, stratosphere has ozone, and where is the ozone layer present? Somewhere in between troposphere and stratosphere, somewhere here. Somewhere, this is stratosphere troposphere boundary. Somewhere here will be your ozone layer. After this comes mesosphere. This is famous for meteors and mesospheric clouds. After mesosphere, we have the thermosphere. This layer has ions. This is called as the ionic layer also. This is stratosphere has ozone layer. Thermosphere has ions. That's why in thermosphere you will also come across auroras here. Now these figures called aurora australis and aurora borealis. Aurora australis is down under close to Australia, and aurora borealis is which is happening currently in around Scandinavian countries. Finally, exosphere. Now, our International Space Station, many of our research projects of the space takes place around thermosphere and exosphere. So, when you have to revise, just pause the video here and see whether you are able to identify what is taking place in each of the layers. So, the bottommost layer, troposphere. After that is hot air balloons, and ozone is somewhere here, stratosphere. Above that is mesosphere, meteors. Then auroras are present in thermosphere. Finally, your space shuttles and these orange dots are solar winds. This is exosphere, the outer layer of our atmosphere. That's all you need to know for your revision. Now, we stood at a place, we looked up. Now we look down. So down, I have divided into two layers. One is the compositional layer and other is the mechanical layer. In the compositional layer, it is the chemical composition which plays a part. Just three things you need to remember: crust, mantle, and core. So crust is made up of mostly oxygen, silicon, aluminium. Mantle is made up of iron, magnesium. Mostly, now this is not uh, written in stone that this is how it is. Mostly, most of the materials are this. Core is nickel and iron. When we look at the mechanical, this is more important. On top we have the lithosphere, that is the crust region, lithosphere. Below the lithosphere is the asthenosphere. Asthenosphere is some part of the crust and most part of the upper part of the upper mantle. Now mantle is divided into upper and lower mantle. This is the upper mantle, this is the lower mantle. So the upper part of the upper mantle consists of asthenosphere. This is not a completely solid state, not a completely liquid state. Somewhere in between, like oil, extremely viscous, extremely plastic. And this also, remember that the entire lithosphere is floating on top of asthenosphere. This will help you understand the plate tectonics better. So lithosphere and asthenosphere, lithosphere is floating on top of the asthenosphere. Below the asthenosphere we have mantle, and then we have the outer core, which is completely liquid and completely watery liquid, and below that we have the inner core, which is a solid ball. This is how it actually looks like. Inner core completely solid, after that is outer core. Outer core is completely liquid. Then we have the lower mantle. Above the lower mantle is the upper mantle, and over here somewhere is your asthenosphere. It is not shown in the diagram here, but the upper mantle, upper part of the upper mantle has asthenosphere. And finally we have the crust. Again, when we are supposed to revise, you can pause the video and try to fill it up yourself. Top is crust, then comes asthenosphere, then comes mantle, lower part mantle or whatever mantle you want, outer core and inner core. This is just a revision that is going on. All this is necessary for what we are trying to do at the end. We are trying to compile everything at the end. So this is the entire idea of Earth, about whatever we have. We have exosphere on the top, layers of atmosphere. Then we have the thermosphere. Then we have the mesosphere. Then stratosphere, and finally troposphere. Yes, I have not gone through that how temperature changes in each of the layers, because that is in depth and we are just revising here so that you can understand maps along with the physical properties, along with the oceanic currents and everything later. And when we go below, then we find lithosphere, asthenosphere, mesosphere, outer core, inner core. Now this mesosphere is inside. That layer is also called as mesosphere, but what you need to remember is it is mostly mantle. UPSC does not recognize this mesosphere. UPSC recognizes this as mantle. So now we go to tectonic plates. There are three types of plate boundaries. Most of you will be knowing this. It is called the divergent, convergent, and transform. Divergent is when plates divert away from each other. Convergent is when they compile, they compress against each other. And transform boundary is when they are sliding past each other. That is a parallel kind of a situation that is flowing past each other. A very good example of this is the San Andreas Fault of California. Why this is most famous? Because a lot of earthquakes in the California region of America takes place because of transform boundary. So how is this divergent plate boundary forming? Now what happens is, first there is a continental crust, just a normal continental crust. Upwarping takes place first. Magma starts pushing upwards. It starts breaking the continental crust into two parts. This is where Rift Valley is formed. An example of a Rift Valley, the Great African Rift Valley. I'll show you how this is taking place in Africa in the next slide. Then a linear sea is formed, the current Red Sea. That is a linear sea that will turn out to be a great ocean millions of years from today. And finally, a huge ocean is ready with a mid-oceanic ridge in the middle. So how this is working out? You see in Africa, just focus on this map over here. This is how it will look like in future. So one line here, this is a nascent sea forming. In today's Africa, if you look at your map, you will find a number of lakes in this region. Now these lakes will eventually coalesce or come together and join like this. This is the nascent sea which we talked about. This is step 3 actually, this linear sea or the nascent sea. This is over here. And finally, this will become a huge ocean. This is moving towards this side. So the Great African Rift Valley has this line, a Red Sea line, and another line which touches our Gulf of Khambat or Gulf of Kutch, sorry. Here also you can see how this is forming, different branches of the Rift Valley. Now, divergent plate boundary and seafloor spreading. The important part over here is seafloor spreading. Convection cells are the reasons how these plate boundaries either diverge from each other or come together. So what happens here? We know that there is a rising convection cell. Now these convection cells are mostly formed because of some magnetic activities taking place in the core. So over here, whenever we have a divergent plate boundary, remember that the arrow will be diverging away from each other, going here and going here. In order for this to happen, something has to push up. So the magma is always pushing up and moving around to form the divergent plate boundary. And this is called as the seafloor spreading. Now there are different evidences of seafloor spreading which you can look at the NCERT books. Over here we are revising and just going through as fast as possible. Asthenosphere, as we remember, as we have revised, asthenosphere is a liquid, semi-plastic or a viscous kind of a state. That's why there are cells forming here. It's moving more like a liquid and it is pulling apart continents. What happens at convergent plate boundary? Now, ocean-ocean convergence. Okay. So in ocean-ocean convergence, one oceanic plate is converging with another oceanic plate. When this happens, the heavier oceanic plate will sink below the lighter oceanic plate. So if we are colliding, for example, this is not happening, just giving an example, Pacific Ocean, okay? This is the Pacific Ocean and this is the Indian Ocean. For example, these two are colliding against each other. So we know Pacific Ocean is heavier. So Pacific will sink below the Indian. Okay. So when this happens, oceanic plate is going below another oceanic plate, ocean-ocean collision. First thing that forms is volcanoes. And these volcanoes results in the formation of island arcs. Not a single island, always island arcs. And thirdly, earthquakes are always common. Whenever plate boundaries are involved, earthquakes are always involved. Now, why island arcs are formed? See, when one oceanic plate is getting under another oceanic plate, melting happens. So the extra magma, where will it go? It moves up. It moves up, creating these volcanoes. And these volcanoes, they spew out the magma, the lava, which solidifies, creating islands. And the plate boundaries are so huge, they are so vast that single island never forms. Island arcs keep on forming. For example, look at the map of Japan. Look at the Pacific Islands. They are all in a single line because there is a plate boundary and ocean-ocean collision is taking place. Pacific Ocean is getting subducted under another part of the ocean. over there the South China Sea or the East China Sea, resulting in the formation of island arcs. So island arcs plus volcanoes formation. Another trick, remember that whenever there is a liquid involved, ocean, volcano will be involved. When there is no liquid involved, then there will be no volcanoes involved. So ocean, there is a liquid involved, so volcanoes will be present. Ocean continent collision. Liquid is present, ocean, so we will have volcanoes. Ocean continent collision, volcanoes will be forming. One very good example of ocean continent collision is the Andes Mountains of South America. Second, young fold mountains will be forming. Oh yes, another thing before I forget, trenches will always be there. In ocean continent collisions and ocean collision, trenches will also always be there. Again, ocean is getting subducted under the continental plates. Oceanic plates are always heavier than continental plates. We will revise it again. Oceanic plate getting under continental plate, melting happening, extra magma, magma moving up, creating volcanoes and young fold mountains. Whenever ocean is involved, volcanoes are present and trenches are present. Similarly, over here, trench will always be there. Ocean is present, liquid is present, that means volcanoes, that means trenches. Ocean is present in ocean continent, that means trenches, that means volcanoes, along with the continental formation of fold mountains. Now we have continent-continent collision. There is no ocean, so there is no volcanoes, and because there is no ocean, there are no trenches. So what do we have here? In continent-continent collisions, no subduction takes place. The plate is trying to get inside, it's trying, there is a subduction, there is an effort, but it's not happening. So when they are not able to get subducted under each other, what they do is they move up, and that's how fold mountains are formed. Fold mountains are formed here, and of course there are no trenches, so what do we have? We always have earthquakes that are ready. Always remember, you can always write earthquakes are present in every single plate boundary, whether it is divergent, whether it is convergent. So this is convergent plates, continent-continent collision. Now let me show you what is happening across the world, and this is how we will be revising geography completely. Transform plate boundary, where I said on the Juan de Fuca plate, this is the transform boundary that is happening. You see, parallel to each other, resulting in huge number of earthquakes and disturbances over there. Now, ocean collision over here. This is ocean, very active plate. This Japan plate over here and the Pacific plate over here, extremely active. So what is happening here? These two are getting collided, resulting in formation of island arcs, and Japan is full of volcanoes. This is also ring of fire. When you look at the map of ring of fire, you can Google it right now, and you will see how it is almost on the boundary with the Pacific plate, because the Pacific plate is getting subducted inside this Eurasian plate. Or there is another plate over here. This is resulting in the formation of island arcs. Now, ocean continent collision right over here, South America. Andes, look at the map of Andes mountains and how this is in one single line. So again, this oceanic plate is getting inside the South American plate. Now, ocean is involved, that means volcanoes are involved, that means trenches are involved. Look at the trenches around the South American, around the eastern border of South America, western border of South America. You'll find some amount of trenches here as well. Similarly, one of the deepest parts of the earth is not in the middle of the Pacific Ocean, but it is around these trenches. Mariana Trench is somewhere here. Finally, continent collision is taking place over here. India, of course, Himalayas, cold mountains, and as we are in Delhi, we are in North India, we know the huge amount of earthquakes that take place in this region. Okay, so let's move ahead. So what did we have? Okay, yeah, divergent plate boundary. I did not show you divergent plate boundary. It's over here. There is a Great African Rift Valley over here. There is also a divergent plate boundary that is taking place in this area. So we have the ocean collision, we have the ocean continent collision, and we have the continent collision. Ocean collision, what is involved? Ocean is involved, which is liquid. That means volcanoes will be present. That means trenches will be present. Ocean continent, again ocean is present, that means volcanoes, that means trenches. Now earthquakes are common in all. Continent collision, there is no liquid, there is no subduction, nothing is happening. Plates want to, but they are getting up. That means fold mountains. So wherever fold mountains are present, continent is here as well. So fold mountains are also here. Okay. So I think we have covered almost all. These are small tricks which you should remember. Ocean, liquid, so what will it lead to, etc., etc. Now, wind and current. This will be taught continent wise. I'll tell you how we are going through. But first understand the heat budget, how heat is distributed. Sun does not send heat equally across the earth. It's not possible, it's not happening. So what is happening? So, winter solstice, short day in northern hemisphere. Why? Because the sun's rays are directly coming towards the Tropic of Cancer. Comes to summer solstice. Sun's rays is directly coming to Tropic of Cancer. Over there Capricorn, over here Cancer. Now twice a year equinoxes happen when sun shines directly over the equator. So heat does not get distributed evenly, it is always uneven. And that results in the formation of wind systems or planetary winds. So planetary winds are global winds occurring in belts that go around the planet, and because of the Coriolis force also this changes. There are three most important wind belts: trade, westerlies, and polar easterlies. Rotation of the earth is responsible for Coriolis effect. Because of Coriolis effect, the winds do not go straight, they turn. How do they turn? They turn like this. So, on the equator, sun's rays falls, resulting in what? Resulting in low pressure region. That's why this is called equatorial low. Wind rises and moves towards the poles, but when the wind is moving towards the poles, some forces act on it and it falls, creating high pressure region in 30 degrees north and south of the equator. Somewhere around 30 to 20 degrees north and south of the equator, subtropical high forms. So subtropical high forms here. Now subtropical high. Now high pressure is formed. Whenever high pressure is formed, winds will move away from high pressure. Remember, winds always move from a high pressure region to a low pressure region. So wind is moving away right here and over here. Now the wind that is coming here, this completes the Hadley cell. So equatorial low, wind moves up, goes around, falls here, and then goes back. So this is completing the Hadley cell. What happens on the other side is the subpolar low. Wind goes here. Now look at the polar high. Again a high pressure region, again wind goes from the high pressure to a low pressure region. So wind has started moving here. Now when both of them are colliding, 60 degrees north and south of the equator, 60 degrees north, it hardly receives any sunlight. So of course, due to sun, there is no low pressure being created there. But a low pressure is being created because of the movement of these two regions, because of the movement of these two winds. They're colliding against each other and moving up, just like the formation of fold mountains. When they're moving up, this results in the formation of polar cells. And this completes your ferrule cell as well. So northeast trade winds, always the winds are named from the direction they are coming. Whenever you are confused, just draw this diagram and just draw north, south, east, west. So this wind is coming from the southeasterly direction, so it is called southeast trade winds. Now this is coming from the northwesterly direction, north, south, east, west. So that's why this is called the northwesterlies. Okay, from the direction the wind is coming, it is named after that. I hope this is clear. And how equatorial low is formed: sun falls on it and winds rise. Equatorial low is formed. Then that wind moves towards the poles. Some forces act on it and it falls around 30 to 35 degrees north, creating a high pressure zone over here, 30 to 35 degrees, called the subtropical high. Now when the wind falls in the subtropical high, it creates a high pressure. So wind flows in two directions. One as northeast trade winds completing the Hadley cell, and another towards the subpolar low. When it is moving towards the subpolar low, it meets the polar easterlies, another high pressure winds coming from the polar high. These two collide, resulting in the formation of subpolar low. So my office hours are always present for you guys. If you have any confusion, you can always join and ask me in the office hours. Now we are moving towards the ocean currents. What do we have here? You see, ocean currents are also extremely important for the formation of deserts and other landforms. We will just study one, and along with that we can construct the others. So we have the Gulf Stream here, a warm ocean current. The equator is right over here. This is the equator. Warm ocean currents always start from the equator and move towards the poles. Cold ocean currents always start from the poles and moves towards the equator. So Gulf Stream moving from here, and this is moving also because of the landforms as well as due to the Coriolis force of the earth. This is going here, it is meeting the Labrador current, and we got here the Grand Banks, a fishing ground. Another UPSC favorite question is the fishing grounds. So this is one where the warm and cold currents meet. These two meet, forming the North Atlantic drift. A Norwegian current moves up, and another current, a cold current, goes here. That's the Canary current. Now Canary current is very important for the formation of the desert conditions in Sahara. This completes the North Atlantic gyre. This is called a gyre. Now when we take a mirror image and flip it down, then we can get the South Atlantic gyre. How? So we had the Gulf Stream going here, Labrador current meeting here, and this forms the North Atlantic drift. Canary current is coming here, and North Equatorial current, counter current it is called. Flip it. Brazil current, another warm ocean current just like the Gulf Stream. Another current is coming from here, mostly the Falkland current, but a polar current as well. A Canary current is coming from here, so another current has to, a cold current is coming from here, Benguela current. and a south equatorial countercurrent is flowing here. So this completes the South Atlantic gyre. You need to practice this more and more in order to understand how this forms. You see, Brazilian current is going over here, South Atlantic current, it's meeting the South Atlantic current, and we have the Benguela current, and South Equatorial current is coming here. So now we flip this and towards the Pacific Ocean. So what is happening in the Pacific? We have the Kuroshio current, a warm ocean current going here. From the north, that is an Oyoshio current. So Kuroshio, Oyoshio. How do you remember this? Oyoshio has the word O in it. Cold also has the word O in it. That's how you don't get confused. So Oyoshio is a cold current, Kuroshio is a warm current. Both of them meet here, forming another fishing grounds over here. So now we come to this region, the other half of the Pacific. Oyoshio was going somewhere there. Over here we have the California current, and California current finally meets up over the counter current. Similarly, South America. South America, we have the East Australian current, a warm oceanic current. Peru or Humboldt current, very important for El Nino La Nina. And another cold ocean current will be meeting up here or going in the other direction. So these are always circles and gyres which are called. Antarctic circumpolar current is going from the south. It is meeting the Peru current over here. Similarly, the East Australian current, again the West Australian current. You see another thing. The western parts of each continent has a cold oceanic current. West Australia, cold current. Peru, cold current. Benguela, cold current. Canary, cold current. California, cold current. Western part of each continent will have a cold current. Now, how do we compile the two? From the equator, when there is a rising Hadley cell in the equatorial region, results in the rainfall in a daily basis, resulting in equatorial forests. Where they fall? They fall in 30-35 degrees north and south of the equator, resulting in the formation of high pressure region along with the cold oceanic currents, which we read right now, leading to the formation of tropical deserts. So the whole idea of this revision and this orientation is to make you understand how we will be covering each portion of the earth, understanding how it looks the way it looks because of the oceanic currents, the planetary winds, and other factors responsible for its creation. When we study Australia, for example, next class will be on Australia, what we'll be studying is why could Australia not have looked the other way? We'll be studying how all of the South Equatorial currents and East Australian currents are forming, how each of these ranges are formed, and this way you remember it forever. You will never be able to forget it. How these oceanic trenches have resulted in the formation of these islands. This is an extremely active plate. So that's our whole idea. Take each part of the continent and just show how its maps were formed, how the oceanic currents were formed, have formed and resulted in the creation of it. Thank you.